Hola, chaps. Let's learn. Hola, chaps. I want to go over the aerospace engineering quiz from February 28th. I know I've returned it to you, but there were some issues I kind of just wanted to clarify with you how to do it. So on the quiz, you have this back. Those of you who haven't seen the quiz, well, it's based on astrophysics and aerospace engineering, but you can try to follow it along. So while studying photographs of star Betelgeuse, Team Kunhanima, which is a combination of Kushi and Hana and Fatima, discover an Earth-like planet orbiting Betelgeuse. They estimate the planet's orbital radius and name it Kumbaya. Calculate the orbital period in Earth years for this planet. All right, well, even the CP physics students have had that particular equation. So to do it, I have, oh, you can't quite see that very well. So I have the radius given. A little hard to see, but okay. Oh, that's too bad. That's better. All right. And the mass given. And I'm supposed to find the orbital period and express the answer in Earth years. So the equation to use comes from Newton's version of Kepler's third law, where the orbital period squared is equal to 4 pi squared times the radius cubed divided by the universal gravitational constant divided by the mass of the object that you are orbiting, in this case, the star Betelgeuse. And you solve for t, the units will be meters for the distance, not kilometers. The mass has to be in kilograms, not grams. And your time period t will work out to be in units of seconds of time. And I got 400,400,000 seconds. Now, the problem states express the answer in Earth years. And if you don't put it in the units that they ask for, then you're going to get dinged. So there are 3,600 seconds in an hour, 24 hours in a day, 365 and a quarter days in a year. And so that works out to 12.7 Earth years is the amount of time it takes for Kumbaya to orbit the star Betelgeuse. All right, so that's how you do that one. The next question was, further analysis using an advanced telescope invented by Michael indicates planet Kumbaya has a mass and a radius given. Devon proposes placing a laser rangefinder in orbit around Kumbaya, facing downward to act as a laser altimeter. We have a beautiful map somewhere in the science building of the surface of Mars that was generated by a laser altimeter looking downward on the surface of the planet and pinging it and measuring how much time it took the light to go down and come back up, and using distance equals rate times time or speed times time, calculate the surface elevation of the planet Mars. And it became a nicely detailed map. But here, part B. So if the laser were placed on a satellite orbiting Kumbaya with an orbital period of 240 minutes, what would be the height of the satellite above the presumably smooth surface of Kumbaya? All right, so to answer that one, a little sketch to remind you that the orbital radius is equal to the radius of the planet plus the height above the surface of the planet. So this is another one that CP physics students should be able to solve. You have to convert to 240 minutes into 14,400 seconds of time. And now you use the mass of the planet, not the mass of the star. Suppose I could make that a little bit larger for you. Even so, right? And solving for r this time, because the period t is given. So rearrange, and algebraically r is the cube root of gmt squared divided by 4 divided by pi squared. When you plug all that in, I got 16,400,000 meters, which is 16,000, I'm rounding, 400 kilometers. Now, the problem specified what is the height of the satellite above the surface. So you have to take the orbital radius, subtract from that the planetary radius, and what's left is the orbital height. So the radius of the planet was 6,987 kilometers. You have to convert the radius that you calculated for the satellite, orbital radius, into kilometers, subtract kilometers, and if you round it off early, then you'd end up with 9,410 kilometers. If you don't round off till later, you get 9,375 kilometers, which you should round off. 9,380 kilometers would be pretty good. So that's how you do those first two problems from that quiz. Let's see if I can zoom in a pinch more, huh? All right. Next quiz question, part C, calculate the atmospheric density at that altitude. This one is strictly an aerospace engineering problem. None of my physics students have had it. In engineering, we have reference book, which is many sheets, and somewhere on one of the back pages, the section on aerospace has the formula for calculating atmospheric parameters. So this says for an Earth atmosphere, the temperature as a function of height is equal to 15.04 degrees Celsius minus this linear term, 0.00649 times the height in meters. All right, so first you calculate the temperature. Then the pressure at that altitude is equal to 101.29 times this term here that you can maybe make out. It says the temperature from the previous calculation plus 273, really should be 0.15, divided by the gas constant, 288.08, and then raise all of this to the exponent of 5.256. Plug that in, and you'll get the atmospheric pressure at that altitude. And then finally, the question that I asked you on the quiz, calculate the atmospheric density at that altitude. The density is equal to the atmospheric pressure divided by this term that says the gas constant, no, 0.2869 times the temperature at that altitude plus 273.15 degrees. So what we're doing is we're converting the temperature from a Celsius scale to a Kelvin scale as we plug it in. Now, earlier in the school year, I challenged you aerospace students to write a computer program so that you don't have to do these three steps. During a quiz, you could just run the program. You should have done that, but either way, the result that you end up with should have been 0.044, I said that wrong, 0.4459 kilograms per cubic meter. All right, so that's the result I got for part C. Part D, if an airplane flies continuously at 28 miles per hour, how much time would it take in days for it to circle Kumbaya at its equator at an altitude of 9,395 meters? So, again, a little sketch that says, I need the circumference of the circle, but the circle is the height above the planet, and the planet has a radius. So the radius of the circle is like an orbit radius. It's the radius of the planet plus the height of the airplane above the surface of the planet. So adding those together and then rounding off to the nearest kilometer, that's 6,996 kilometers. Circumference is 2 pi r. Now the airplane, so that worked out to be 43,957 kilometers. Now for the airplane, distance equals speed times time. The speed was given as 28 miles per hour, but these are kilometers. So you have to either turn the kilometers into miles or you have to turn the miles per hour into kilometers per hour. I decided I'm just going to use the conversion factor that 1 mile is 1.609 kilometers. So I multiplied 28 miles per hour times 1.609, and I get 45.1 kilometers per hour. Now I can solve for how much time it takes to fly around the planet once. It's 43,957 kilometers divided by 45.1 kilometers per hour, and I ended up with 977 hours. Of course, the quiz specified give the answer in days. 24 hours in a day, this works out to 40.7 days. The last question, based on the astrophotography tracking platform project. So if you want to take a picture of Betelgeuse as it moves across Earth's sky at night, if the exposure is for 30 minutes, through what angle will the star move during 30 minutes? To solve that one, note that the Earth rotates once in 24 hours. So 24 hours goes through an angle of 360 degrees. You can set up a ratio that says half an hour is to 24 hours, as the angle x through which the Earth rotates is to 360 degrees. Cross multiply, solve for x, and you get an answer of 7.5 degrees. It's a little late to get this quiz debriefing passed back to you, but better late than never.